Hello learners, you are welcome to Eco Learner Support for NECO and WAEC candidates. I am your physics instructor for this class and will be taking expansivity. Follow me as we go.
Eco Learners Support, a support program of the Lagos State Ministry of Basic and Secondary Education for WAEC and NECO candidates.
Like I said, we are taking expansivity. So let's look at the scope of coverage for the expansivity for this class. We'll look at the meaning of expansion, the effects and application of expansion. Also, we'll be talking about linear expansivity. So the objective here is that at the end of this lesson, there's something you have to achieve. It is that you should be able to explain expansion. You should be able to highlight the effects of expansion. More so, you should be able to define expansivity and solve some simple questions that has to do with linear expansivity. Now, the word expansion. When we say expansion, what does it mean? It means increase. It means it has left the initial size, something else has been added to it. So when we say expansion is the increase in size of a substance. So here, generally, when solids are heated, expansion takes place, they increase in size. Now, let's look at the effect of expansion. When expansion occurs, what effect does it leave? Let's look at it. Well, as we are looking at the effect, we'll also be checking it side by side with the application. So I will tell you the effect and where we apply it. Now look at it. Expansion causes cracks in building and bridges. So since we know that expansion will cause crack in building and bridges, then we will need the knowledge of expansion in building and bridges. In building structures and bridges. Let's take for instance, you observe that for all the bridges you have, there's always an interval where you have metals here like this. So if you have a long bridge, you will see that there will be an interval here where you have metal. And that is where if you are in a car, you will always hear a particular sound once the car gets there. What happens is that space is being considered, that space is there because they've put into consideration the effect of linear expansivity. So that space is to accommodate the expansion that will take place when the bridge is heated. So if that bridge is just made to be straight, once there's expansion, it will start cracking. But because of the knowledge of linear expansivity, that space is left. So once it expands, it fills up the space. If it contracts, it comes back to the normal size. So we know that it's going to cause crack, and we have made provision, that is application for it in buildings and in bridges. Not only that, the bulging of railway track. So all your railway track is always straight line. But you will observe that railway tracks always have the same way it happens there. It happens in railway track. There will be space, a particular small space. The reason is that when the temperature is high, that the metal used for the railway track will bulge out, will increase in size. If this space is not here, the railway will just bulge out like this. So it will not be straight again. It can cause the railing of the rail. So what happened here is that this space is left here so that once there is increase in the size of the rail, it fills up the gap. So you still see it as a continuous track. But if you did not know the effect of expansion by bringing about bulging, you wouldn't be able to make provision for this space to fill in that gap. So effect of expansion is that it brings about bulging of railway, and the application is that we are able to make provision for that space that we cater for that bulging. Now, the third part, the sagging of telegraph wire. So telegraph wire is such that if you have it like this, or let's assume you have the wire from here to this place now, once the temperature is high, it will drop, it will sag this way, it will sag this way. So that is what happened because there is an increase. So once the size has increased, you will see that it will drop down a little bit. So that is what we mean by sagging of telegraph wire. Now the fourth one, cracking of a thick glass cup. If you have a glass cup and then that's more reason why you don't put your glass cup in your freezer. You can put it in the fridge to make your drink chill, but you don't put it in the freezer. Why? Because the temperature will be too much and it will make your glass cup to crack. If you put it in the freezer, by the time the temperature of the freezer reduces, then the glass will respond by wanting to shrink. So as it wants to shrink, it gives way and then the glass cup will crack. So that is also the reason why you don't put bottled drink. If it is glass bottle, you don't put it in freezer. Because if you do that, before you know it, by the time you open your freezer, you meet it broken because of expansion. Now the last part that I'm going to talk about under the effect and application of expansion is the use in bimetallic stripes in thermometers and thermostats. You would have observed this, that while you are using your pressing iron, you usually hear a particular sound. That sound is as a result of thermostat. What happened is this, I'll show you. Look at this. If you have a thermostat is bridging. This is where the current is coming from. And this is it bridges this point. So as this becomes hot, it expands. As it is expanding, it expands upward such that it leaves a space here. Once it's leaving that space, that is where you hear that sound. So it stops the current from flowing, it stops heat from being produced. So you will see that once you set your iron to a particular heat that is needed for that iron, for your clothes, once it gets to that level, you hear that sound, it trips off. And then once it's cooling, it drops back again. Once it's cooling, it drops back again to that point to allow current to continue to flow, so heat is produced again. So it is an automated form of cooling and heating. It controls the amount of heat that you have. That is why while you are pressing your clothes, the iron is not continuously hot. It's hot at a point, as it is not increasingly hot. It increases at a point, but once you get to a particular level, it retains it. That is brought about by the use of thermostat, and the same thing, it is the same bimetallic stripe is used in thermometers to measure change in temperature. Let's go to the next part. Let's talk about linear expansivity. From the word linear, linear means we are looking at what happens on a straight line. So if you have a straight line here, what happens on this straight line, the expansion that takes place along a straight line is what we call linear expansivity. If you have a rectangular surface, now you can look at this part, this is linear. You can consider this part, it's linear. But when you are considering the two, that is area, we'll talk about that later. So, but here we're looking at linear expansivity, a straight line expansion. So there's a definition for that. Linear expansivity of a substance is defined as the increase in length per unit length per degree rise in temperature. So that is linear expansivity. So from here, mathematical relation, linear expansivity is defined as what? Increase in length. Hold on, I just told you now that for expansion to take place, it means there's an increase in size. And for you to talk about increase in size, it means there's an original size and there's a new size, which means that there's a difference between that two sizes. That difference is what we call the increase in length. So which means that there's an original length that is existing. Let's say we have L1 before. And then when you heat it, there's an expansion, you have L2. So the difference between the first length and the second length is what we call the increase in length. So we usually represent it by using the symbol we call delta L. So then original length, which is L1, then change in length, change in temperature, delta theta. So this change in length is the second length or the new length minus the original length, which is L1. Now, change the temperature, we say that the new temperature, which is theta 2, minus the old temperature, theta 1. So that is what you have it on this place. Now, let's go to the next part. Now, linear expansivity. So, if you say linear expansivity, like I said it in that place, it is increase in length over original length times change in temperature. Look at this. The linear expansivity is what we use the alpha symbol to represent. The increase in length is that the second length, which is the new length, minus the old length, which is L1, times original length. The original length is L1, then change in temperature is delta theta. And change in temperature is theta 2 minus theta 1. Usually, we make use of this formula a lot. Then, how did we arrive at the formula? I'm going to show you so that you don't cram. Once you know how we arrive at it, I'll give an explanation from this point, how we arrive at this, so you don't need to cram the formula. Look at how I'm going to give you the breakdown to that now. Look at this. So, I said that I will show you how this formula came to be. L2 equals to L1 into bracket of 1 plus alpha delta theta. So you don't need to cram this formula. You'll be making use of this in most of your exam, like your WAEC and your NECO. So from the definition, you say alpha equals to linear expansivity. From the definition of linear expansivity is talking about increase in length over original length, then change in temperature. So you go this way by saying alpha equals to change in length, means there is a new length and the difference between the new length and the old length all over the old length times change in temperature. So from here, we can decide to make L2 the solution of the formula. If you cross multiply, L2 will be equals to L2 minus L1 will be equals to alpha L1 delta theta. You close it this way. So from here we can say L2 minus L1 is equals to alpha L1 delta theta. So from here L2 equals to L1 plus alpha L1 delta theta. So we can now get our L2. L2 equals to L1 into bracket 1 plus alpha delta theta. So you can see now that this formula we started from this place. So you don't need to cram. The only thing you need to know is the definition, which says that linear expansivity is increase in length per unit length for every degree rise in temperature. At another time, this is when they ask you to calculate the new length. The new length is L2. At another time, they can ask you to calculate the change in length. If you are asked to calculate change in length, you still go back to the original formula, which says that alpha equals to change in length over L1 delta theta. So if you are asked for change in length equals to alpha L1 delta theta. So mere cross multiplying will give you formula to go with that. You can also be asked for the old length if you are given change in length. So from here now you can say L1 equals to alpha delta L rather over alpha delta theta. So you can use this formula, you can also use this formula. But all of these three, 1, 2, and 3, all emanated from this one. So you don't need to cram all the formula, just know the definition, be able to produce this formula, then you can make use of it to solve any problem. Now, let's look at what we have next. I want to take some examples here. I will want you to bring out your calculator because we are going to solve some problem. So I will also bring my calculator because I'll be punching the calculator so I can show you how we arrive at the solution. A copper wire, question example number 1, whose length at 30 degrees Celsius is 10.0 meter. So you look at it. When you are solving a problem that involves use of formula, you look at what you are given and what you are looking for. Which formula relates them? That's all you need. Look at it. The length, that's the original length. what the temperature that is given, the original temperature also will be your original temperature. So original length is 10 meters. And it's, what temperature was that given? That is 30 degrees Celsius. Now, is heated to, so there's a new temperature, that's theta 2, that's 50 degrees Celsius. Now, find the new length. So we are looking for the second length. When the linear expansivity, alpha, is 0.000017 per Kelvin. Now, let me comment on this. The SI unit of linear expansivity is per Kelvin. So, which means that, at another point rather, it can also be written as per degree Celsius. So, this can be done interchangeably because both Kelvin and degree Celsius have the same fundamental interval. So, the change that you experience in Kelvin is going to be the same change you experience in degree Celsius. So, the SI unit is per Kelvin. When you have it as per degree Celsius, it's still fine. You can go with it. So, let's come back to this question. Find its new length. We are looking for the new length, and that new length is L2. So, from the definition of linear expansivity and from the other one we just did, look at it, let me show you again. From this part, look at this. L2 equals to L1 into bracket of 1 plus alpha theta theta. Remember, you got it from this formula. So, we can make use of that to continue with our solution. Look at this. So, from here now, calculate the new length. The new length is L2. L2 equals to L1 into bracket of 1 plus alpha theta close bracket. So, our L2 will be equals to L1. What is the L1? That is 10 into bracket of 1 plus alpha. Alpha is given as 0.000017 times change in temperature is our delta theta. Delta theta means theta 2 minus theta 1. What is theta 2? Theta 2 is 50 minus theta 1 is 30. So 50 minus 30 is what? 20. So in that case, delta theta is now 20. So you're going to have 20 here. So that being the case, L2 equals to 10 into bracket of 1 plus. So you multiply. Please don't forget, don't mix it up, because at times you might know what to do and not know how to do it. In this case now, the multiplication of alpha and delta will take place before you add it to 1. Please take note. Don't add 1 to 0.001017 before multiplying by 20. So you multiply by 20. So if you do that, 0.000017 times 20, use your calculator, you confirm that you're going to have 0.00034. This is what I have from my own calculator. So if you have it this way, then L2 will be equals to 10 into bracket. Now you add 1 to it plus 1. You're going to have 1.00034. So from here, you multiply this by 10. So when you multiply 10 by this, you're going to have 10.0034. The unit we're given is in meters, so you report back in meters. So from this question now, we have been able to get the value for the new length, which is L2. Additionally, you can also be asked to find the change in the length. The change in the length is just the difference between the two lengths. So the first length and the second length, what's the difference? If you are asked for change in length, that will be the second length then minus the first length. The second length is 10.0034, then in first length is 10. So when you subtract this, you're going to have 0.0034 meters. So whichever way you are asked, so you should be able to oscillate between them. Let's look at what I have for you to do. You know, it's nice for us to interact. So you have this, and I want you to take it within the next 1 minute. All right. So now that you have attempted it, a brass rod, 2 meters long, and all of that information is given, let's look at how to approach it. So the answers on the way. Look at number 1. A brass rod, 2 meters long, at a certain temperature. What will be the length for a temperature rise of 100 Kelvin if the linear expansivity of brass is given? So look at the information given here. Look at the information given here. You have a length. The first length is 2 meters, which is correct here. Then the second length is what we are looking for. What will be the length? That's L2. The temperature rise, delta theta, is 100 Kelvin. And then the linear expansivity is given here as 18 times 10 raised to the power minus 16. So you can see now that in the other examples we took, linear expansivity is given in decimal point, but here it is expressed in standard form. So if you do that, L2 equals to, using L2 equals to L1 to bracket of 1 plus alpha delta theta. So you are going to have the value, you replace the value of L1. L1 is 2, so you should replace the value of L1 here. Then alpha is given here, that's the linear expansivity, we replace it here. Then delta theta, which is 100, comes here. So when you multiply this, 118 times 10 to the power minus 6 times 100, use your calculator, you are going to have this. So this value now, add it to 1 first before multiplying by 2. And take note, let me emphasize again that you are multiplying 100 by this value before adding 1. Not that you add 1 to this value before multiplying by 100. Don't make that mistake. So once you have this value, add it to 1, you have this. Then 2 times this value will give you this. So the new length now of that brass will be 2.0036 meters. That is for the first part. Let me also emphasize this, that before you solve any problem, bring out the values you are given. Know what you are looking for. Now pick a formula that relates what you have with what you are looking for. Makes it easier for you to get your solution done. So having said all of this, in case you have question, you have comment, you have observation, please put everything up through to us using the social media handle that will be displayed on the screen. Thank you for listening.
Acing your WAEC and NECO examinations has been made easy by the Lagos State Ministry of Basic and Secondary Education with the ECO Learner Support for WAEC and NECO Candidates television program. Join seasoned teachers as they take you through these core subjects: mathematics, English language, physics, chemistry, and biology, targeting the exact syllabus of WAEC and NECO. Watch ECO Learner Support for WAEC and NECO candidates on this station. Learners can also connect with ECO Learner Support for WAEC and NECO candidates through these social media platforms to access more educational content and give their feedback. ECO Learner Support for WAEC and NECO candidates. Pass your examinations with flying colors.